Hey folks, so today we are going to talk about transforming raw scores. Maybe. Okay, there we go. So, as you've likely forgotten or haven't, which is awesome, all normal distributions are the same when we convert them into a standard score. So, if we measure everything in units of standard deviation and center around the mean, we get a standard score. So why do we do it? Well, simply because it allows us to put everything in the same metric. So we can convert any variable into that same metric along the standard normal. Now, changing these units and essentially converting in between units is called standardization or rescaling. And simply stated, a standard score is a raw score that has been converted from one scale to another, where the latter scale has some arbitrarily set mean and standard deviations. So why convert to a standard score? Well, standard scores are more easily interpretable. We can convert between metrics, but with a standard score, the position of a test taker's performance is relative to other test takers, and it becomes very easy to compare with that score. For example, on the SAT, each section's at 800, or at least it was back in the day. So knowing what the total score is out of, as well as being aware that the standard deviation is 100, means I can put anybody's standardized test score in context relative to a standard normal curve. And eventually, you'll get good enough at this where you can convert between the two if you work with standardized scores often. You'll notice that when I give examples for effect size, I tend to convert them almost instinctively into IQ score points, because I found that that is an easy metric for me to conceptualize the magnitude of effects. For example, a 1 standard deviation increase in anything is the equivalent of a 0.15 IQ bump. 2 of those takes you from being average to Mensa. 4 of those takes you from Mensa to being developmentally disabled. So just giving some kind of frame of reference. So different systems for standard scores exist. We'll cover a couple of them. I've already talked about, well, you'll see they come up in my language a lot. And each standard score is unique in terms of its mean and standard deviation. So I'm going to cover Z-scores, talk a smidge about T-scores and Stanines and some other standings. I can't talk today. Some other standard scores. Regardless of the score type, you can think of a score scale as essentially 0 plus or minus 1 scale. Because most standard scores tend to have a mean of 0 and a standard deviation of 1. Okay, so let's just talk about rescaling for the Z statistic. So a Z-score is the result of converting from a raw score into a number that indicates how many standard deviation units the raw score is above or below the mean of that distribution. I've got 2 equations on the slides here illustrating what it looks like for a sample and a population. In case you forgot, sample is with Roman letters, population is with Greek letters. The Z from the sample comes from your actual data, while the Z from the population comes from the population, which we never had. But before I keep getting sidetracked, in essence, a Z-score is equal to the difference between a particular raw score and the mean divided by the standard deviation. So, just to note, because apparently people still make this error a lot. So when you are rescaling or transforming data into a Z-score, it keeps the same shape of the distribution. Only the numbers change. It's not like reshaping it at all. It may move the scale, so it may look like it gets a little longer or taller, but the rank order is the same and the shape of your underlying distribution is the same. So any linear rescaling where all you're doing is multiplication, division, and addition and subtraction, none of those are going to change your raw score distribution. When we get to nonlinear transformations, that's where it gets funky. And if anyone's interested, I'm happy to talk with you during office hours, or you can pop over to my data science for psychologists class. So only the numbers change when you're rescaling in a linear transformation. So there are a lot of advantages here. So they allow us to compare scores on a common metric. They set the origin to be 0, the mean, and this allows us to essentially look at everything relative to the mean performance. And the units are all in one standard deviation. So +1 means you're 1 standard deviation above the mean, +2 means you're 2 standard deviations above the mean, -2, -2 standard deviations below the mean. And it allows us to compare measurements across scales. You can compare across and know if you are a more taller person or a more geared person relative to those scores. Now, just to emphasize this, because it comes up all the time, the shape of our distribution doesn't change when you rescale. It doesn't. We can go from z-scores to raw scores to z-scores, you name it, we can do it. So how do we interpret a z-score? So a z-score results from the conversion of a raw score into a number indicating how many standard deviation units that raw score is below or above the mean. I know I've reiterated this a lot, but it is one of the most core essential concepts that we are going to lean on in testing. If I could only have us learn like 3 statistical concepts and from all of your time in psychology. Correlation, z-score, and the third one, eigenvalues. Eigenvalues probably one we haven't covered yet. So let's just focus on the first 2. Z-score and correlation, most important things. Knowing that someone obtained a z-score of 1 on a spelling test, for example, provides way more context for that score than knowing that somebody obtained a raw score of like 65 on a spelling test, because you don't have any information to compare it to. What's a 65? Who knows? Could it be 65 out of 65? Yeah. Could it be like out of 650? Could also. So it doesn't tell us a lot. And that's problematic. So that's why standard scores are pretty popular. So with a z-score of 1 on that spelling test, we know a lot more. So we can draw on our knowledge of areas under a normal curve, for example. So we would know that only about 16% of other test takers performed higher on that test without knowing a 1 standard deviation above it. Again, by contrast, a 65 is meaningless because it just doesn't have any information whatsoever. There's almost an implicit that maybe it's 65 out of 100, and sure, you can kind of do, but that's a risk. Okay, so there are lots of z-scored examples out there on how to interpret standard scores, how to work them. You've covered them in your other classes. I'm happy to walk you through one-on-one if you really want it. And don't feel shy. I've got office hours for a reason. But standard scores are important. Z-scores, knowing how to convert in between the two so that you can get a frame of reference is really important. So on that note, we're going to wrap up on some of that kind of refresher on raw scores. So I'll see you in a bit.